Welcome to Ogo Reviews. In this video, we're going to be looking at acids and bases as it relates to organic chemistry. So let's dive right into it. In order to understand acids and bases, there are two definitions you need to be conversant with. The first one was coined by Bronsted and Laurie. And how they defined acids was that acids were proton donors. So they defined them as proton donors. And of course, bases were considered as proton acceptors. Let's illustrate this with a generic example. If you have a species HA that is reacting with water in an equilibrium reaction to produce hydrozonium ions and an anion A-, let's see which one acts as an acid and then the one that acts as a base. So this species on your left donates this hydrogen to that water and will now be considered as the Bronsted-Lowry acid. The water that accepts the proton will be considered as the Bronsted-Lowry base. Let's go on the right. There are two species that are produced which are in equilibrium with the reactant. The hydrozonium ion has the ability to give a hydrogen atom or a proton to the anion to produce the HA. In this case, this is going to serve as a Bronsted-Lowry acid on the right, and this is going to serve as the Bronsted-Lowry base on the left. I've put this in inverted commas because there is a proper terminology to describe these species. So what is the right terminology? The acid on the right is referred to as the conjugate acid. And as the name suggests, it's a conjugate, so it goes together with something else, right? So what does it go with? It goes with this base over here. So the conjugate acid is always coming from the base. And it only differs from it by one hydrogen ion. It's always like the case. There's always one hydrogen ion difference between the conjugate acid and its base, or the conjugate base and its acid. So of course, by extrapolation, this will be the conjugate base. And this conjugate base will be the conjugate base for the acid on our left. And we know that a lot of anions are considered as bases in organic chemistry. And a lot of cations or protons are considered as acids. So this is something we need to keep in mind as we go on. Second, we're going to look at the Lewis definition of acids and bases. So Lewis, acids, and bases. So how did Lewis define acids and bases? He defined acids as electron pair acceptors. And then he defined bases. So bases were defined as electron pair donors. So let's illustrate this with a very interesting example where water reacts with itself in a reversible form to produce hydrozonium ions plus OH- ions. So we can illustrate and show all the lone pairs of electrons, since acids were defined by lone pairs and bases also by lone pairs. Don't forget that the hydrozonium ion will have a plus charge. So every time that it has a plus charge, one of the lone pairs will be used up. But then again, the lone pairs on this hydroxide ion will be more than just two. We're going to have three of those. So if you follow what is going on, then you realize that this water was able to accept a lone pair donated by that water. So we have water 1 and water 2. The water 1 was able to give one of its hydrogens to water 2. And when that happened, it produced the hydrozonium ion. And all that happened was that the lone pairs here was given to this hydrogen that had no electrons. And when that happens, it produces a positively charged hydrozonium ion. And because the hydrogen left some lone pairs of electrons with it, so it produces a negative charge on the hydroxide ion. So in that case, this becomes the Lewis acid and this becomes the Lewis base. And the same thing here, hydrozonium ion can donate or it will accept a lone pair from the hydroxide ion, and therefore the hydroxide ion can also be considered as a Lewis base. No more the conjugate is going to be a Lewis base, and this is going to be a Lewis acid. We can illustrate this definition with a reaction between aluminum trichloride and ammonia. That will give us aluminum trichloride ammonia. So let's see how this reaction happens. And of course, there will be charges. So that will be a plus on nitrogen and minus on aluminum trichloride. You first of all draw the Lewis structure. So aluminum will have 3 chloride elements attached to it. And it's going to react with nitrogen that has 3 hydrogens attached to it. Of course, there's going to be a lone pair. Now, in this case, aluminum doesn't have an octet, so it's very electron deficient. So it will accept the lone pairs of electrons that will be donated by ammonia. So this lone pair will be shared with aluminum, and that will give us something that looks like this. So aluminum trichloride with all the chloride ions will be engaged in a reaction called the dative reaction, dative covalent bond reaction, where even though there's a sharing of electrons, is more to the aluminum because aluminum is very electropositive. So it tries to pull the electrons towards itself. And therefore, you're going to see that this nitrogen will be positively charged and the aluminum will be negatively charged. And this will be the product. But then remember, Lewis acids are electron paired acceptors. So therefore, aluminum trichloride will become our Lewis acid. And ammonia, which donated electrons, will become our Lewis base. There are several Lewis acid base reactions in organic chemistry, so it's something that we need to pay attention to. Next, let's look at how acids and bases compare in terms of their strength and what are the factors that actually influence the acidity or the basicity. The first item we're going to look at is what we call the pKa value. This value is unique to the compound. It is just the negative log of the Ka, which is the same as log 1 over Ka. So you can clearly see that there's an inverse relationship between the Ka and the pKa. When the Ka number is low, the pKa number goes up, and the vice versa. So what that means is that if I have an alcohol that has a pKa value of about 17, and I have water that has a pKa about 14, what I can see is that the Ka value of the alcohol is way less than the Ka value of water. That's what I can tell. The better the Ka value, the more acidic that particular molecule will be. So I can tell that the Ka value of water is higher than the Ka value of the alcohol. So therefore I can tell that the water is going to be more acidic than the alcohol. In the same vein, if I have an alkane with a pKa value of about 15, I have an alkyne that has a pKa value of about 25. I have an alcohol with pKa value of 17, and I have a thiol that has a pKa value of about 13. Looking at these numbers, you can clearly see that the thiol is going to be most acidic, and the least acidic will be the alkane because the pKa value of the alkane is very large. In the same way, you can compare that the alkyne is going to be less acidic compared to an alcohol, and it will be more acidic compared to an alkane. So what if you don't have the pKa value? Then you have to look at the stability of the conjugate acid, stability of conjugate acid or base. So how is this related to the strength of an acid? Well, if you have a generic acid like HA that ionizes in water to produce a hydrozonium ion and a conjugate base A minus. When you have a very stable conjugate base, so let's say this conjugate base is very stable, what it means is that it can actually tolerate this minus charge or the negative charge on this A. That way it doesn't react with the hydrozonium ion to go back into its acid form and the water. So what we are saying is that you actually want this forward reaction to be greater than the backwards reaction. And in order for that to happen, if you're able to stabilize this conjugate base, then there's no tendency for it to react with the acid to get back the unionized acid and the water. So if you have a stable conjugate base, then this acid is going to be a strong acid. So having a stable conjugate base kind of indirectly tells you that you have a stronger acid. The same way, if you have a base B that has all these lone pairs and it reacts with a proton in a reversible reaction to give us a B ionized with a positive charge on here, what we are saying is that if this B atom or element is able to stabilize the positive charge such that you have a forward reaction that is stronger than the backward reaction, then we're going to say this is going to be a stronger base. So that is how the stability of a conjugate acid or a base relates to the strength of an acid or a base. In either case, the conjugate acid or base that is produced needs to be stable. So the next series of things you're going to look at is what factors actually influence the stability of the conjugate base or the conjugate acid. In order to understand the factors affecting the stability of conjugate acid or base, we might have to understand what electronegativity is and the size of an element. So let's take a look at the periodic table. As you go down the row in the periodic table, such as carbon, nitrogen, oxygen, and fluoride, electronegativity, which is a measure of how an element pulls electrons towards itself, tends to increase as you go across the periodic table. However, as you go down the column, such as fluorine, chlorine, bromine, and iodine, electronegativity tends to decrease. So electronegativity will decrease as you go down the column. So we know that as you go across, the size doesn't increase tremendously. So you have 6 to 9. So size is not an issue. But as you go down the column, size increases. So size increases. Now let's see how that affects stability of a conjugate acid or base, especially a negative charge. So if you have a negative charge on a conjugate base, you might want to distribute that negative charge so that it's stable. In a sense where you have electronegativity increasing, you have the negative charge also being more stable with a more electronegative element. However, if you go down during this, looking at the size, even though electronegativity decreases, size becomes a predominant factor. So size overrules the electronegativity as you go down on the periodic table. So what that means is that bigger size will be able to stabilize the electrons more. So let's look at what that means. So you have a fluorine atom which has a smaller size, and then let's say you have something like a bromine atom that will have a larger size. If you had a negative charge, it will be more concentrated in the fluorine compared to the bromine. So the bromine is going to have the negative charge, distributed in a larger space. So the negative charge will be moving around in more larger space, and hence the stability of bromine anion will be much better than that of a fluoride anion. So these are factors that you need to look out for when you're comparing the stability of a conjugate acid or a base. Now let's illustrate this with an example. So if I had a structure of a base that has an alkoxide. So I have an alkoxide, which will be, in this case, it will be ethoxide. And I have a thiol. So it is an ethylenate or a thioanion. We want to compare which of these two will be more stable. So looking at this, oxygen and sulfur belong to the same group in a periodic table. So we know that the size increases and electronegativity decreases. So electronegativity decreases, but size increases. And we already know that when you go down the periodic table, size becomes a major factor. Maybe oxygen will be like this. Sulfur is going to be twice as large, right? And therefore, if you have a negative charge on oxygen, it's kind of more concentrated than when you have it in sulfur. So this will be easily stabilized in the sulfur compared to the oxygen. So we will predict that thionylate will be more stable than the ethoxide conjugate base. And therefore, any acid coming from this ethoxide will be unstable, will be less acidic compared to an acid coming from a thionylate. So we will predict that if you have an acid like this, which is the conjugate acid for this base, you predict that that will be more acidic. So this will be more acidic than that one. So another example can be when you have a carbon that has a negative charge versus when you have oxygen with a negative charge. So we wanted to compare these two groups and see which one will have a better stability in terms of anion. So if you take a closer look, you see that in this form of the structure, the anion is sitting on a carbon, and we know that carbon does not tolerate anion or a negative charge very well compared to an oxygen. So we will expect that this will be less stable compared to when an anion is in the oxygen. So this will be more stable because remember, carbon and oxygen, carbon is more electropositive and it doesn't attract the electrons very well. So we had carbon, nitrogen, oxygen, fluoride, and we said that as you go from the left to the right, electronegativity increases. So electronegativity increasing means oxygen will be able to take more electrons than carbon. So we expect that this will be more stable compared to that. So these are ways to compare the stability of a conjugate acid or a base. In example 3, we're going to look at which of the highlighted protons is more acidic. In order to solve this question, you have to determine what are the conjugate bases of each one of the protons. So I'm going to represent this structure in two forms. So I'm going to look at when you have this hydrogen removed and what is the conjugate base that you will form. So if I did that, this is what I'll have for the proton that is right here. And also if I remove the other proton, because remember the difference between the conjugate acid and its base is just one proton. So if you remove the proton here, then you have this alcohol, but then there will be a negative charge on this carbon. Let's compare these two species and see which one is more stable. Looking at this, we realize that the negative charge is on this carbon here, and on this species, the negative charge is on the oxygen. So species A and species B. Looking at oxygen and carbon, which one will stabilize the negative charge much better? We already know that oxygen and carbon are in the same row on the periodic table. So we know that as you go across the periodic table, electronegativity will increase. So oxygen will be more capable of adapting a negative charge compared to a carbon. And because of that, we expect that the negative charge on the oxygen will be more stable than the negative charge on the carbon, and therefore we expect the proton on the oxygen to be more acidic than the proton on the carbon. So this will be more acidic than the proton on here. Another factor to look at is what we call resonance stabilization. At this point, if you don't know how to draw resonance structures, you refer to the video on resonance structures. So resonance stabilization of the conjugate base plays a major role when it comes to the strength of acids or bases. Let's illustrate this with an example. If I had structure A, which is this acid, and I had another structure which is an alcohol, both of them are 2 carbon structures, you realize that the hydrogens that are highlighted will have different acidity strengths. So let's compare them. Let's draw the conjugate base for these compounds. In order to do that, you only remove the hydrogens that we are talking about. So if you did that, that will leave us with this species with negative charge on the oxygen. And here you're going to have the ethoxide conjugate base. Let's look at the stability comparison for these two. In order to do that, you realize that the negative charge is found on oxygen in either cases. So size and electronegativity doesn't play a role. However, there is a component called resonance that plays a role. So let's focus more on structure A. In structure A, you realize that you can actually draw resonance structures for the carboxylic or the carboxylate. So these lone pairs of electrons, we have 3 of them, can be moved to this sp2 bond, and that will flip the pi bond over there to give us these resonance structures. And remember, they're double arrowed, and that will give us oxygen with a negative charge on there with 3 lone pairs of electrons, and a double bonded oxygen with 2 lone pairs of electrons. So looking at this, you realize that you can actually write resonance stabilization for the carboxylate, but you cannot do that for the conjugate base of the alcohol. So this is more stable because electrons can actually move around. More stable conjugate base compared to this conjugate base right here. So the more stable the conjugate base, the more acidic its corresponding acid will be. So we will expect that this structure will be more acidic than the alcohol. In example 2, we are comparing cyclohexanol and phenol. So cyclohexanol and then phenol. You want to know which one is more acidic. In order to do that, you have to draw the conjugate base of each one of them and see which one is more stable. So let's try and draw the conjugate base for cyclohexanol. The conjugate base of cyclohexanol is going to look like that with a negative charge on the oxygen. And the conjugate base of the phenol is going to look something like this. So it has an oxygen right here with a negative charge on it. Now let's compare the stability of these conjugate bases. You realize both of them, the negative charge is residing on oxygen, and therefore electronegativity and size doesn't matter. However, stabilization by resonance plays a major role. You can clearly see that the phenoxide ion can resonance stabilize by moving these electrons around, as we're going to see in this resonance stabilization. So as you can see, you can write as many as about 4 different resonance structures for phenoxide. And that makes this electron on the negative charge very stable. Therefore, we expect phenol to be much more acidic than cyclohexanol. Example 3. Which is more acidic? Is it this acetic acid or this phenol? In this case, both compounds can actually resonance stabilize. So we're going to compare which one is going to be more stable than the other. So as we've been doing, we're going to write a conjugate base for these acids. So if you did it for the carboxylic acid or the ethanoic acid, you're going to have something that looks like this with 3 lone pairs of electrons on this oxygen. If you did it for the phenoxide, you're going to have something that looks like this. Now let's try and write the resonance structures for both of them. And I think we've previously done it for both of them. So I'm going to speed through it. So as you can clearly see, you can write so many resonance structures for phenol. The interesting thing is that the negative charge for the ethanoate is shared between 2 oxygen atoms. And we know that negative charges are best stabilized on oxygen atoms compared to sharing the negative charge amongst about 1, 2, 3 carbons. So if you compare the stability of these resonance structures, I would say that the ethanoate stabilization is better compared to the stabilization of the phenoxide. So therefore, we will say that the ethanoate is going to be more acidic compared to the phenol. Once again, what we're trying to say is that even though you can write more resonance structures for phenoxide, in this case, the negative charge is actually shared around or is moved around on carbons. You have 3 different carbons that is sharing the negative charge, as compared to when you have the ethanoate where the negative charge is shared between 2 oxygens, which is way better than when you have a negative charge on a carbon. Remember, carbon cannot really tolerate a lot of negative charges. Oxygen, however, can tolerate a lot of negative charges, making the ethanoate anion or the conjugate base more stable compared to the phenoxide conjugate base. And therefore, we will predict that the ethanoic acid will be a much stronger acid than the phenoxide. Another factor to look at is what we call inductive effect. So inductive effect is basically looking at how certain groups are able to pull electrons from an electron-rich area. So for instance, if I had an oxygen and a carbon bond, I expect that the oxygen, because it's very electronegative, will pull electrons towards itself. So it will have a partial negative and the carbon will be partially positive. This pull of electrons is what we call induction. Let's take an example to illustrate inductive effect and acidity. So example 1. Let's compare acetic acid and trifluoroacetic acid. If you watch closely, we're trying to see which one is going to be more acidic. The factors we've described so far, which includes which atom that a negative charge relies on, which also includes resonance stabilization, might not play out in this case. Let's see. The first thing we want to do is to write the conjugate base of the 2 of them. So if you wrote a conjugate base of trifluoroacetic acid and acetic acid, this is what you're going to get. You realize that you can write resonance structure stabilization for both of them. Also, the negative charges on these 2 oxygen, so both factors that we've talked about might not hold. However, the only thing that holds is this trifluoroacetic acid and this CH3 group here that can make the difference. So what happens is that as the methyl group tries to give electrons, because carbon tends to be more electropositive, it will kind of destabilize the negative charge because you're giving more electrons onto the oxygen, and that makes it even more destabilized. However, The trifluoroacetic acid has a lot of fluoride or fluorine atoms that are very electronegative. And so what happens is it tends to pull these electrons towards itself. And that pulling of electron towards itself makes this negative charge stabilize, because then the negative charge is able to move a little bit around the molecule. So meaning that the more stable the conjugate base, the more acidic this trifluoroacetic acid is going to be. So we can therefore say that trifluoroacetic acid is more acidic than acetic acid. A very important thing to note is that inductive effect falls off as the distance increases between the negative charge and the group that is pulling the electrons. Let's illustrate this with an example. So if I have this kind of acid and I have two fluoro groups on the third carbon, so you can see the carbon number 1, 2, and 3. And then I have another acid that has the fluoro group on the second carbon. So you can see this is carbon number 1, 2, and 3. Which of these two is going to be more acidic? So like I mentioned, as the group that is doing the pulling kind of has a longer distance from the negative charge, the ace effect becomes very small. So let's write down the conjugate base for these acids. So if you wrote down the conjugate base, this is what you're going to get. You have two fluoro on here, and the conjugate base for this acid will look like this. So now we want to see which of them will be more stable. You realize that the electronegative group here will be pulling electrons towards itself. But guess what? It will be doing it from a further distance compared to what will be happening in this particular compound. So we will expect that this will be more stable. This will be more stable compared to that one, because the group doing the pulling is a little farther away, and therefore the negative charge will kind of be more localized compared to what you see in this molecule. Which of the highlighted protons is more acidic? In this example, we have to write the conjugate base for when each one of the hydrogens is removed. So to make life easy, I'll label this as hydrogen A and hydrogen B. So if I remove the hydrogen A, this is what I'm going to get. I have this oxygen with a negative charge, with a trichloromethyl group, and I'll have the hydroxyl group at that position. And if I remove hydrogen B, I'm going to be left with something that looks like this. Trichloromethyl group with an OH group. So in this case, the only difference is the fact that the trichloromethyl group is closest to this oxygen A as compared to the oxygen B. So let's see how things go. In either case, the negative charge is residing on oxygen and there's no resonance. The only factor to look out for would therefore be inductive effect. So looking at the first species, we realize that the trichloromethyl group will pull the electrons on the oxygen towards itself, and the impact will be felt highest because it's only separated by one bond. Whereas if you look at the other species on this side, the inductive effect, which is the pulling effect of the trichloromethyl group, which is the electron withdrawing group, is a little far away. So the tendency for this electron to be delocalized or pulled is relatively less compared to that. And therefore, this will be localized. The electron here will be more localized compared to here. And we expect this to be more stable because of that. So this will be more stable than that one. And because the conjugate base is more stable, it makes this hydrogen more acidic. So hydrogen A is going to be more acidic than hydrogen B. The last thing we want to talk about is the effect of orbitals on the stability of a conjugate base and how that relates to the strength of acids. To illustrate this, let's take an example. So if I have a double bond here with a hydrogen, and I have a triple bond at the terminal with another hydrogen, we want to find out which of these two hydrogens is going to be more acidic. To do that, let's write the conjugate base for when each one of these hydrogens is removed. And for simplicity, I'm going to label these hydrogens as hydrogen A and hydrogen B. So when I remove hydrogen A, this is what I'm going to get. I'm going to get this double bond with a negative charge on there. And of course, there will be lone pairs of electrons. And this is going to give us the triple bond with a hydrogen. The other conjugate base will be when I have the double bond with a hydrogen and when I pull the hydrogen on hydrogen B. So when I pull hydrogen B, I expect to get a negative charge and of course with lone pairs of electrons right there. Now let's see which of these two conjugate bases is going to be stable. Of course, you can write resonance structures for any of them. And also the negative charge is found on the carbon. And there isn't anything about inductive effect in this case. So the only thing that we need to worry about is the hybridization state of the carbon or the atom that is bearing the negative charge, and especially when it comes to carbons. So if you watch closely, the negative charge is born on a carbon that is sp2 hybridized here. And when you come here, the carbon is sp hybridized. Now there's something called the S character, which we already talked about earlier. If you don't remember that, please go and review your hybridization states. So you have S character and a P character. So the more P character you have, the more the tendency that the electron is going to be unstable. And the more S character you have in the orbital, the more stable that particular electron is going to be. So electrons are more stable when you have more S character than when you have more P character. So when more P character is less stable. So looking at these two, let's look at the percentage character of S and P in each one of them. You can clearly see that when it comes to sp2, the S character is about 33%. And when it comes to the sp orbital, the S character is about 50%. Because you have half of S and half of a P. Over here we have 1 out of 3 orbitals. So sp3 is made up of 3 orbitals and 1 out of it is made up of S. So this gives us 33%, that's 50%. So we expect that the triple bond is going to have more S character. It's going to have more S character than the P character. And therefore we expect the negative charge of the triple bond to be more stable than the negative charge on the double bonded carbon. And therefore we anticipate that the hydrogen number B is going to be more acidic than the hydrogen number A.